Hello everyone. In this video we are going to talk about figuring out the angle between two vectors and the dot product. So we're going to start with what is hopefully an illustrative example here. So we're going to work with vectors u and v in R3, and so you can just assume that u looks like u1, u2, u3, and that v looks similar with coordinates v1, v2, and v3. So we're going to start with these two vectors. I'm just going to, draw random ones here. So we'll have u here, and v is going to look like this. And we are interested in this angle between them. And so what I'm going to do is kind of complete a triangle here, and I'm going to do this. And I claim that this is u minus v. So how might we draw u minus v generally, right? So we could concatenate minus v, which looks just like v but pointing in the opposite direction, with u, and then we would do u plus minus v, right? So we could do something like this, and we see that this guy in blue is exactly the same vector as the one completing our triangle up above. It just has a different starting spot. Okay, so I'm just going to call this side A, this side length b, and this side length c here. If you remember from back in the day, at some point you probably saw the law of cosines, which says that c squared is a squared plus b squared minus 2ab cosine of theta. So we already know how to compute length of vectors. So what's this really saying here, right? This is u minus v, this vector. Its length squared is the length of u squared plus the length of v squared minus 2 times the length of u times the length of v cosine theta. Okay, and what do we want to do? We want to solve for theta, right? We want to get this by itself. So we're just going to look at both sides and kind of expand things out. So if you kind of simplify the terms, we know how to use the distance formula, and we're squaring, so the square root's going to go away. It actually looks not too terrible. All right, and so we get this. Again, we want to do some more simplification, and after the next step, you're going to see we can do quite a bit of canceling. All right, so this is, a lot of algebra here, but what cancellations do we see? Well, I've got my u1 squared here, my u1 squared here, v1 squared, v1 squared, u2 squared, u2 squared, and it turns out all of these guys end up canceling. And so what we're left with is negative 2 u1 v1 minus 2 u2 v2 minus 2 u3 v3 is this term with the angle included. Okay? And so we can divide by negative 2, and we end up getting this right here. And so if we want to solve for theta, we just take arc cosine of each side, and it looks like this. So this may not seem very special, but this numerator here actually has a name. Okay, so I just want to point out that when we look at these two vectors, that what we're doing is we are pairing via multiplication each of the corresponding entries, right? So first entry times the first entry plus second times the second plus third times the third. And this just so happens to be what leads to our definition of the dot product. So the dot product just generalizes the idea we just saw. So if we're in Rn here, right, so I have these two n-dimensional column vectors, then I just do the same thing where I pair them off term by term with multiplication. So u dot v, this is the dot product, is u1 times v1 plus u2 times v2, and you keep going until the last row plus un times vn. Okay? And this allows us to, again, generalize this notion of the angle between vectors, and it works just like we saw in the three-dimensional case. So our general formula for the angle theta between vectors u and v and Rn is going to be, again, we want to do the arc cosine, and we'll just take the dot product up top because that is exactly what we had in the three-dimensional case, over the product of the lengths of the two vectors. Okay. So one thing that I'll point out here, and we won't get into details, there is something called the Cauchy-Schwarz inequality. And it says that the dot product is going to always be less than or equal to the product of the magnitudes of the two vectors. And it also tells you when they are equal, that's going to be if and only if one is a scalar multiple of the other. So basically they have the same direction. Why is this important? Well, arc cosine is a function. We want to make sure that these things that we're inputting are really in the domain, right? And so we know that cosine of theta should be between +1 and -1. And so we better have that this inside is between -1 and 1 if we're taking arc cosine of it. And this inequality ensures that that's true, right? My numerator is no bigger than my denominator, so I'm always going to be between -1 and 1. All right, so let's do a couple of examples just to see how this works. So let's let u here, this will be an R2, be 1, 0, and v be 0, 1. Okay, so in this case, first we want to figure out their lengths, right? So that we know that, or I guess you could do the dot product first, it doesn't matter, we have to do both. So this is just the square root of 1 squared plus 0 squared, that's 1. V has the same entries, just in a different order. That's also going to have magnitude 1. And u dot v, well, that's just going to be 0, right? It's 1 times 0 plus 0 times 1. So this is saying that theta is arc cosine of 0 over 1, which is 0. Well, when is cosine 0? That would be pi over 2, right? And so basically this is saying that they have a 90-degree angle. Does this make sense? Well, what are these two vectors? So u is 1, 0, so going 1 in the x direction, and v is 0, 1. And yeah, sure, the x and y axes are at a 90-degree angle with each other, so that makes sense. All right, so let's do one more example here. So in this case, it looks a little more complicated. So I'll just do u dot v this time first. So we have 1 times 1 plus 1 times -1. That's going to be 0 combined, plus 2 times the square root of 6/5. All right. And so this is just 2 times the square root of 6/5. So for the length of u, we have 1 plus 1 plus 4. The squares of each of those, all under the square root, so square root of 6. And the length of v is going to be 1 plus 1 plus 6/5, which is 16/5, again, under the square root. Okay, so we end up with arc cosine of something that apparently looks terrible, but we'll see it's actually not that bad, because what is the square root of 6 times the square root of 16/5? Well, we can rewrite the 16/5, right? That's just 4 over the square root of 5. So really, we have like a square root of 6 over the square root of 5 times 2 times 1 over the square root of 6 times 4 over root 5. So we have another root 5 up here if we do the reciprocal, and times 4. So these guys cancel, these guys cancel. Oh wow, this is actually just 1/2. When is cosine 1/2? Well, that's when the adjacent side is the shorter one, right? And so that means that theta is going to be pi over 3, right? If it were root 3 over 2, it would be pi over 6. All right, and I am just giving you one exercise this time, although it has 3 parts. So I just want you to find the angles between these 3 pairs of vectors. Thank you for watching.